Welcome back here. This video looking at the electronic structure of atoms. These are our flame test notes and able to describe how flame tests work. So question is, what happens when someone switches on a neon lamp? That's kind of where we're going with this. Boiled down to pretty much electrons get excited, they emit light, and once they do that, they drop to a lower energy back down to a lower energy level. And this can all be described by our quantum theory, or that quantum model of atoms. Before we get there, though, we need to talk about light as waves. So the first part, electromagnetic radiation. All waves, including what our eyes see, are in the form of electromagnetic radiation. So all types of energy can be seen as a wave. All of these waves are traveling at the same speed. So 3 times 10 to the 8th meters per second. The only thing that's different about them is their wavelength and their frequency. So wavelength, distance from 2 points to adjacent points on a wave. So I picked the 2 tops, but I could have easily picked this point here and this point here. And then frequency is the number of waves that pass a point in a given second. So if you think of this gray line here as being 1 second, in this case the frequency would be 2. So 2 waves pass in 1 second. Alright, electromagnetic spectrum, like I said, not only includes visible light, but also things like X-rays, microwaves, your cell phone, the frequency it runs on, things like that, your radio, and it's all dependent on frequency and also wavelength. Things you need to know, low frequency things have long wavelengths. So these waves are big, 100 meters long for some of these things. I'm trying to think here. This scale on the bottom is in terms of frequency, but still these on the order of about 100 meters long. Down here you're talking negative, something really small, like negative 10 to the 15th or 10 to the negative 15th or so in terms of wavelength, meters long, so really small. So low frequency, these have long wavelengths. These don't hurt us at all, so they have really low energy, something you need to know. The other thing you need to know then is high frequency have really short wavelengths, which also means they have really high energy. We call this ionizing radiation. So what that means is it's actually so much energy that it can start knocking electrons off from our cells, from the atoms in our cells, which then some of those things start wanting electrons back and they steal them from other things. This is how we get DNA mutations and stuff like that. This stuff down here is not good. Gamma rays are the reason why. Not that we want to become the Incredible Hulk, but because of like nuclear radiation and stuff like that. That's in terms of gamma rays. Same thing. Reason why you can't go to the doctor and just get X-rays all the time is because it's a part of that ionizing radiation. It'll cause damage to your body. All right. So talking a lot about light as waves explains other things like reflection. And using mirrors, refraction. So why is it that if you're looking in water and you go and like try to grab a fish or something like that, that it's not in the exact spot as what it looks like through the water? That's refraction. And then the other one is Doppler effect. Astronomers use this. It proves a lot of really cool things, but you have experienced this. Think about you're standing alongside the road and a motorcycle's coming, and then the motorcycle passes by you. That change in the sound is the Doppler effect. So it sounds different as it comes in as a high pitch, and then as it goes away it's a much lower pitch. That's the Doppler effect. The thing is, though, waves can't explain everything. In terms of, if we view light as a wave, it doesn't work for things like the black body radiation, which will explain, all of these things we'll explain here in a second. Photoelectric effect, and then emission spectra of elements, which is what we care about, those flame tests. We call this the dual nature of light, so the fact that it can be viewed as a wave, but then also for these we actually have to view it as a particle or as a piece of light, which is weird to think about. And our quantum mechanical model actually incorporates all of this. So the reason why we have these weird shapes and orbitals is because Schrodinger, the guy who came up with this, took in both parts. He took the fact that light, as well, as well as electrons, can act as a wave or as a particle. All right, so why things glow? First, blackbody radiation is just the fact that you can heat something up, and there's a point at which everything, no matter what it is, so you could heat me up if you want, to a point where I would begin to glow. That's blackbody radiation. So Max Planck said energy can either be released or absorbed by atoms in only discrete chunks, and which he called quantum. So what kind of to think about this a different way is he pretty much said that energy can only be absorbed or released by electrons in these chunks, or that an electron can only be on one of these stairs. Whereas you can't really kind of float in between a stair. Whereas like if it's a ramp, you could be any height from the ground, just depending on where you put yourself on the ramp. On a stair, you can only be this height, this height, this height, nothing in between. So these energies, or these quantum, we said is equal to a constant, which is actually now called Planck's constant, h, times a frequency. And that because it can only exist on one of these stairs, that E, the energy, has to be a certain number. So hotter the object, the more energy, the higher it is on our staircase, or the higher the frequency. That's going to give us certain colors when we do our flame test. And then lower energies are going to give us lower frequencies, which are going to give us a different range of colors. You may have heard of this at, some stars burn white, they're hotter, that's one color, versus some stars burn red, which are cooler, is another color. So the amount of energy determines color. Side note, so based on this, we can actually determine what the hottest temperature possible. So one calculation estimates that that this is the hottest temperature, which is completely ridiculous. It's 1.42 times 10 to the 33rd degrees Celsius. So we call this absolute hot. And it's at this point that everything breaks down. So conventional physics breaks down. Unreal. I mean, we'll never be able to obtain that temperature, but just absolutely crazy. All right, the second thing that tells us that we can't view light as a wave is this photoelectric effect. So Einstein, may have heard of him. He explained the photoelectric effect. So other scientists have seen this before, they just couldn't explain it. So Einstein, kind of building off of what Planck said, he explained the photoelectric effect by assuming that light acts, again, not as a wave, but as a packet, which he called a photon. And kind of building off of Planck's work, he said that a photon, or the energy of the photon, is equal to that equation. So energy times Planck's constant times frequency. Or really, that if you want to think of light, think of it as a stream of particles instead of a constant wave. So these streams of particles come in, and as one of these particles hits an electron on a surface of a flat piece of metal, it can actually knock an electron off. And depending on the energy of that, it could knock an electron off, or if it's not enough energy, it won't. So there's a point at which that energy is great enough to knock one of these electrons off. So what this experiment is, think of a laser pointer, And if you can turn that laser pointer on and off, on and off, on and off, and you can do this so fast, or there's actually a point in which you can't do it any faster, that point would just be a single packet of energy. That's a photon. And then that would and then at the point at which that's enough to knock an electron off, that's where we see the photoelectric effect. All right. The last one, the one we care the most about, is Niels Bohr. So we've talked about him before. So using Planck and Einstein's explanations, was able to describe emission spectra. So what that is I picked hydrogen here. So hydrogen glows. All we're doing is charging it with some electricity. So we have a light bulb that's filled with hydrogen instead. And what we're doing is we're exciting these electrons. And as you excite these electrons, it starts to glow a certain color. And with the naked eye, we see it as pink. But if we pass it through a prism, or like in class, a diffraction grating, it actually breaks up into these certain colors, which is kind of cool. And Bohr made some assumptions. He said electrons correspond to certain energies, or these orbits, so those rings around our nucleus correspond to certain energies. We've seen that, talked about that before. He said electrons have to be at those certain energies, so they can't be those stair steps. They have to be on a stair step, or they have to be in one of those rings. They can't be, it can't be a ramp example. And that, coming from Einstein, this energy emitted or absorbed has to be a certain amount. It has to be the amount of a photon. It has to be that packet. So what Bohr was able to do is he was able to describe this for hydrogen. So he was able to figure out that an electron that was excited to the third level, that falls down to the second, produces red light. Excited to the fourth and back down to the second is green light, and then and so on. We call this the Balmer series. You don't need to know that. Other people kind of helped him figure this out. It was actually a scientist that figured, or not a scientist, a school teacher that figured this out. Also, we only see these 4 lines, but there are a bunch of other possibilities. So some of them actually come out as a UV. So if we look way back to our electromagnetic spectrum, UV is ultraviolet, so that's beyond what we can see. Some of them come out as infrared, which is lower frequency, lower energy than what we can see. And the other cool thing is, there's an infinite number of rings, but eventually there's a point at which that electron, we excite the electron so much that it leaves. We call this ionization energy. So the amount of energy it takes to remove an electron is very much related to this. You just excite it so much that it leaves. All right, so what does this mean for us? Flame tests. So just as we can excite hydrogen, we can excite all of these other elements. And all elements give a specific color. And again, we see the color with the naked eye, but as we break it up with a prism or a diffraction grating, we get those spectral lines. Astronomers use this to help identify what elements are in, stars and galaxies and things like that. So here, emission spectra of all elements. See, some of them have a bunch of lines. You can think about, what would cause that versus, why hydrogen only has 3. All right, so how this works. We excite electrons to get them to move to these higher states. So they start at the ground state, we give them energy, they jump up. They don't like that. Nature doesn't like to be at high energy states. So the electrons lose energy as that electromagnetic radiation. And we as humans can see some of that in terms of visible light. We can build instruments that see it other way, that can see, quote unquote, see it as other ways. And then after it emits the light, the electrons then drop back down to the lower energy, or at least maybe a lower ring, and then drops again until eventually it gets down to ground state, because again, they don't like to be at those higher energy levels. And that is all.